Today we are happy to have Zongchen Chen from CMU will tell us about fast convergence of Markov chains for the global dynamics.
Yeah,
Go ahead.
thank you. Thank you very much. I'll talk about the optimal mixing time for the global dynamics, and this is joint work from with Quick Liu from University of Washington and my advisor Eric Vigoda from Georgia Tech, and so the today's talk will be mainly two parts. The first part is like backgrounds and our main results, and in the second part, I'll talk about the proof approach and techniques of our main results. And so please feel free to interrupt me or ask any questions. And so I'll start with the setting and the problems that we are looking at. So, so I first start with like a toy example for the type of problems that we will study. And let us consider the independent sets of a graph. So I use G to denote a graph and the capital omega to denote the set of the collection of all independent sets of this graph G. And so just recall that independent sets a subset of vertices that contains no adjacent pairs. And also I'll use the red dot to denote the occupied vertices. I mean those inside the independent set, and the blue dot to represent the unoccupied vertices. Those are not included in the independent set. And we will mainly study two types of problem, which are, we'll see that they are actually equivalent to each other. So the first is the counting problem, where our goal is to output the cardinality of the set omega, which is exactly the number of independent sets of your graph G. And the second problem is the sampling problem, which our goal is to generate a sample, generate an independent set of G uniformly at random. And so these are the two problems that we will be looking at. And so first is we notice that this problem can be quite difficult. The reason is that this set omega can be exponentially large in the size of the graph. And to see this, you just consider like a linear size independent set, then every subset of this independent set is still an independent set, which you have a linear, exponential number of independent sets. And also the exact counting problem is known to be Sharpe-Hard. So here the exact just means I want to, the algorithm needs to output the number of independent sets exactly. And the Sharpe-Hard means the computational complexity of like computing the total number of satisfying solution of a set formula. And so just this sentence just means that the exact counting problem is a very hard problem. And the people usually would study the approximate version of these two problems, which I call approximate counting and approximate sampling. So for approximate counting, the goal is to output the account of the number of independent sets with 1 plus minus epsilon to be polynomial in the size of the graph as well as 1 over epsilon. And for the approximate sampling problem, our goal is to generate a sample from some distribution
I'm losing your voice. I don't know if others had the same experience.
Happening to me too.
So
okay,
let's
okay.
continue, see if it persists, and then, yeah. Okay.
Can you hear me now? Or?
Yeah, it was just a couple of times your voice disappeared and came back. So let's
Okay.
continue and see if
be...
it's
Okay. Yeah, it might be my internet Wi-Fi is unstable. So please let me know if it doesn't works now. So I continue. I just introduced like this. The exact counting problem is a hard problem, and people just usually study the approximate uh, algorithm problem, which is the approximate counting and approximate sampling. And so this talk will be mainly focusing on the approximate counting problem and sampling problem. And for independent sets, it is known that for we will consider graphs of bounded degree where the capital delta represents the maximum degree of the graph. And it turns out there are certain type of phase transition for this computational problem of approximate counting and sampling. So in particular, if delta uh, is at most 5, then there is a polynomial time algorithm to approximate the number of independent sets, and also this is resolved by Wise. And meanwhile, if your maximum degree delta is greater than 6, then it is shown to be like there's no polynomial time algorithm for approximate number of independent sets unless MP is equal RP. And this type of result is actually related to a certain phase transitions studied in statistical physics. And so one natural question is like, what will happen when your maximum degree is kind of between delta is 5 and 6? So this is will be better to be understood in the statistical physics model, and so which is the hardcore model that I introduced now. So the hardcore model can be sort of as the counting and sampling problem for independent sets, but with parameter lambda controlling the weight of the independent sets. And so in particular, uh, so lambda would be the parameter called the fugacity, and we will have a partition function, which is a function of which is a polynomial of this parameter lambda, and its value is the sum. You take sum over all independent sets, and every independent set will contribute a lambda to the size of this independent set. And in particular, if lambda is equal to 1, then z of 1, so every independent set will contribute 1, and z of 1 is exactly the number of independent sets of this graph. And also we will consider the Gibbs distribution, which is like a weighted distribution over all independent sets. So it's a distribution over independent sets, and every independent set, the probability density is proportional to lambda to its size. And lambda equals 1, this is exactly the uniform distribution over omega. And so here's an example where we have a graph on 4 vertex, which is cycle. And if you have a single vertex independent set, then it's weighted lambda, and the density is lambda over z. And if you have 2 vertex, then it's lambda square over z. And z is like the normalizing constant of your distribution, and it's the partition function. And we will study this kind of weighted version of 4 independent sets, and the
Excuse me?
counting problem will be, yes.
Is this is Z can be represented as the determinant of some graph-related metrics? Uh,
uh could you repeat, please?
I'm
It's
asking.
unlikely, Leo. The question was whether this partition function Z can be represented as a matrix in terms of the graph. It's unlikely because you saw that this partition function, even when you evaluate it at lambda equals 1, it is a number of independent sets, which is an extremely hard quantity to compute. So
yeah, maybe a permanent and not determinant.
Permanent is permanent. You can represent everything with, because permanent is complete for all counting problems. So certainly you can do it with a permanent, but not with determinant. But you need some reduction. It's not like a direct. There's some reduction. Valiant shows that it's a complete problem. So yeah, you can represent everything you want with permanent, all counting problems that are described this way. Yeah.
Okay.
Yeah.
Yes, it seems perhaps like all the Tut's polynomial can be like all this type of graph polynomial might be represented as permanent or something. Yeah, so I'll move on. So we'll study this the counting problem would now become to compute the partition function z of lambda, and the sampling problem would be try to generate a sample, generate an independent set from the hardcore distribution, which is mu, which is denoted by mu, and so the intuition of this type of problem is that when your lambda is small, then it should be easy because most of time you will, when you generate samples, for example, you will only see small independent set, and the problem will become hard for large lambda because when you have large lambda, you will see a large independent set, and like most extreme case, when lambda is equal to 0, then you don't see any independent set. So the distribution would just be seen in the empty graph, empty set. And if your lambda is infinity, then this becomes a distribution over all independent set of maximum size, which is a hard problem, like NP-hard problem for general graph. And so it turns out that there's also a type of phase transition, which I will introduce very soon. And this computational problem is closely related to the phase transitions studied on infinite regular trees. And so let me introduce the notion of phase transition studied on the regular trees for hardcore model. So we will consider a tree of degree delta. So it's delta -1 array tree, and the height is h. And for this type of tree, consider the hardcore model on it, so the distribution would be mu to the h, denoted by mu to the h. And we will consider the marginal probability. So the probability is that the root is inside when you inside the independent set when you generate from this distribution. And so turns out there's a threshold for the parameter lambda, which is captured by this formula. And when your lambda is smaller than this critical value, what happens is that the probability, the marginal probability, will becomes the same for even high tree and odd high trees. And meanwhile, if your lambda is greater than the threshold, then you will see a difference between the marginal probability for even and odd heights. And the reason you have this discrepancy is that because it's because of the antiferromagnetism or the repulsive property of the model. This is because when you just look at the probability of being occupied, if a vertex is occupied, then all its neighbor must be unoccupied, and its distance to neighbor is more likely to be occupied. So it's contracted or attractive when you are all distance, even distance away, and you are repulsive when you are odd distance away. So that will result in a discrepancy of the marginal for even high tree and odd high tree. And this lambda critical is marks exactly this phase transition where you have the influence from the leaves to the roots. So basically, when your lambda is smaller than the critical point, you will see the correlation of the spin, the condition, the value of the root and the values of the leaves will decay with the height. And if you consider the hardcore model defined on the infinite tree, that's the region that you have a unique Gibbs measure. And also when lambda is greater than critical value, that's the region that the correlation between the root and the leaves will always exist, means that it does not convert to zero when the height tends to infinity. And also you will have a multiple Gibbs measure on the infinite tree. And what's interesting is that this type of phase transition for the model, for the hardcore model on the infinite tree marks the computational phase transition for the sampling and counting problem for bounded degree graph. So if you look at now the hardcore model on the graphs of maximum degree data, and also we look at the corresponding, the sampling problem or the counting problem, then what happens is that when lambda is smaller than the critical value, that's when you have the decay of correlations. You will have a polynomial time approximate sampling algorithm, and this is the result of Wise. And meanwhile, if your lambda is greater than the critical value, that's when you usually see large independent sets and the correlation between vertices does not vanish. And in that region, the computational problem of approximate sampling becomes empty hard. And this is also a result of slide, and later is generalized to other models by the two other papers. And also I want to remark that for the special case of independent sets itself, like unweighted version, which is lambda equal 1, so this threshold lambda smaller than lambda critical just means the maximum degree is less than 5. And also lambda greater than lambda critical is the maximum degree at least 6. So this gives a picture of the phase transition for the computational problem, and how does that relate to the phase transition of the hardcore model on the infinite tree. And so lambda greater than, yes.
Just to, I'm sorry to slow you down, but just to make sure that the phase transition is on the correlation, and the correlation is the probability of having two vertices in the same independent set. Just to, I think
Uh,
I missed what you mean by.
Yes. So the correlation would just be like two vertex. So an event is like if a vertex is in the independent set or not. And for every vertex, you have this random variable, and you look at two random variable and see the correlation between them. And it will the case with the distance between them. And more specifically, we will look at this notion of correlation would actually means run like a vertex to another subset of vertex. And in particular, like for the tree, we look at the correlation between the root and all the leaves. And leaves can be like any configuration, like any subset of leaves as in, and the other are fixed to be not in. And that's what I mean by correlations.
I encourage everybody to do like Lior and slow Zongchen or any speaker down when something is unclear. So just to say again what Zongchen answered, if lambda is high, you are counting, you are weighting the large independent set. Now, in a tree like this, which is bipartite, can you show the picture, Zongchen, of the tree?
Yeah.
Can you go back one slide?
This one?
With the tree. Yeah. If you no, just next, yeah. If you if you want large independent sets, so lambda is high, then in a tree like this, which is bipartite, you will see either all the even layers or all the odd layers. right? So there will be very strong correlation between the root and the leaves. It depends on their distance, whether the distance is even or odd. So that's, and this will be roughly the two different, roughly the two different Gibbs measures. But if lambda is very small and you know the way mostly small independent set, then there will be just small random subset of the nodes of the tree that are independent. So there'll be no correlation between the roots and the leaves.
Yes, yes, yes.
What does
Yeah,
it mean? Have a unique Gibbs measure or multiple Gibbs measures?
What do you want to answer, Zongchen? You mentioned the question was to define a unique Gibbs measure or multiple Gibbs measure.
yeah. So when your lambda is smaller than this threshold,
We cannot
defines
hear
there's
you.
only one. Sorry, can you hear me?
Yeah, now. No.
Okay, so sorry, the Wi-Fi might be unstable. So I'm just saying when lambda is smaller than the critical value, you will have like you look at the infinite tree, there will be a unique Gibbs measure, which is like the hardcore model defined on the infinite tree. And also when your lambda is greater than the critical value, you will see like you will have like multiple Gibbs measure for the infinite trees,
Yeah,
and
but it
also like
Gibbs measure.
yes, like the Gibbs measure for the hardcore model,
Yeah,
Well,
which
the
is
question
like
was what is a Gibbs measure? That was the question.
yeah. So that's like if you restrict to any finite region, and you put any boundary condition outside the finite region, the distribution on this finite region would just be the hardcore distribution, the Gibbs distribution for hardcore on a finite graph, and that would be the like the definition for the Gibbs measure on the infinite trees.
Leo, basically you should think about the example on a bipartite graph where lambda is large. You can have, you know, basically take all the even layers and populate just random subsets of them. But yeah, mostly these, and then you can have the odd ones. These are two very different distributions with almost disjoint supports that you know are stable, so to speak. And in the case that lambda is very small, there's only one. But maybe we don't need a formal definition of Gibbs measure for what is going to follow, right, Zongchen?
Yeah.
thanks.
So we'll be only just studying like a finite graph or something. But this will be the formal definition of the like the phase transition on the infinite graph. Yes. So should I move on to?
Yes, yes.
Yeah. So thank you for the question and the answer. And so yeah, so we will be just studying like this. We will just take this phase threshold for the trees, and the main property is like the like the decay of correlation, which would be important things for us for this threshold. And so for lambda is greater than the threshold, the problem becomes hard. And the lambda is small, you will have like a polynomial time sampling algorithm. And here the little data would be some measure from for your parameter to the uniqueness threshold. And so there's basically like three type of algorithms, and maybe there might be some others, but there's the most like well studied. There are three types. The first is like the correlation decay type algorithm, which basically you utilize the property that the correlation between a vertex and another vertex or another subset of vertex, it will decay with the distance between them. and this is a result of Wise, which he kind of make this property algorithmic and use that property to design a counting problem, counting algorithm. And what he uses is like he used some relation of the from the graph to the corresponding trees of self-avoiding walks, and use that trees and property of the trees to design the algorithm for computing the margin of a vertex. And the second type of algorithm is this polynomial interpolation algorithm, which is given by Barvinock and Pataragis. And the running time for the correlation decay algorithm, the running time is n to some order 1 over little delta times capital delta. And for the polynomial interpolation, the runtime is n to some function of capital delta and little delta, and the function is actually quite large, so it's probably like exponential in the maximum degree delta, and so the overall runtime might be double exponential in the maximum degree delta. And so this type of algorithm uses the zero freeness of the partition function, and it uses some Taylor approximation for the log partition function and truncate it and to use it as approximation. And there's a third type of algorithm. So I only write Glauber dynamics, but there's actually a whole class of MCMC algorithm, which uses Markov chains to generate samples of independent sets. And the Glauber dynamics is just one of them, like what's the simplest of them. And so I introduced the Glauber dynamics very soon. And also there's a bunch of paper for not only Glauber, for Hardness and
We lost you again.
not only recently.
Zongchen,
First paper.
we lost you again. Can you repeat from global dynamics? When you started talking about global dynamics, we lost you.
Oh yeah, so sorry about that. So global dynamics. So there's actually a whole class of global dynamics, a whole class of this MCMC type algorithms, which is a Markov chain to generate samples from the intermittent sets. And so this has been there has been a lot of works on MCMC methods, and also people have given not only for Glauber but for other type of MCMCs, and they try to push the threshold of the region of lambda up to the uniqueness threshold, but this was not been proved until the recent work of Anari Liu, OVS Garvin, which they finally shows polynomial time mixing time up to the uniqueness threshold. And what we do is we improve their result. So their result, the running time, the exponent of the mixing time is a large constant, but we manage to show the n-logging, which is like asymptotically optimal. And so just let me introduce what's the Glauber dynamics. So it's a Markov chain to generate.
Can I ask a question?
Yes.
Yeah, can you show the results in the previous slide?
Yes.
Yeah, you did not mention the dependence on little delta in the also on big delta. Where do they show up?
Yes. Yeah. Sure. I should put it so it will be a constant times n log n.
Okay, that's great.
And yes. Yeah, so currently the constant is like exponential in the maximum degree. So it's like one open problem is like can we get a better dependency of the maximum degree.
Okay.
Yeah, so let me introduce the Glauber dynamics. So it will be a Markov chain, and every step you maintain a configuration and independent set. And what you do is in every step, you will pick a vertex uniformly at random. And so basically, if adding this vertex is okay, it's not okay, then you just remains the same. And otherwise, you just with some probability you add this vertex, and with some probability you remove this vertex. Doesn't matter if it's already in it or not. And so for this example, you pick this vertex, and you are allowed to add it because it's still independent set. So you just you consider adding it with probability lambda over 1 plus lambda, or you just not adding it with 1 over 1 plus lambda, and you make a decision, and you move to the next step where you pick vertex. But this time, so since it has a label that is already in your independent set, so you won't be allowed to add this vertex, and so it will remains the same independent set. And so this defines dynamics or Markov chain to generate samples from the distribution mu. So it's not hard to show that the stationary distribution of this Glauber dynamics would just be the corresponding Gibbs distribution. And the node and so to describe like how fast the MC converge, this is described by the notion of mixing time, which is the number of steps you need to be within 0.01 total variation distance from the distribution mu, even when you're starting from a worst configuration. And so to state our theorem, so it's just that when your lambda is smaller than the critical value, and your graph has maximum degree data, then this Glauber dynamics will converge for hardcore model in n log n steps. So it's a constant times n log n, where the constant depends on maximum degree and the little data. And so this also gives this picture for the phase transition for Glauber dynamics. So lambda smaller than the critical lambda, it will converge in n log n steps. And meanwhile, lambda is greater than the critical lambda, it will require exponential in n steps. And also this is the hard computationally hard region, where you actually does not exist any polynomial time sampling algorithm, approximate sampling algorithm. And so our results actually holds for a lot of models, not just the hardcore models. And what we actually shows is that for the Glauber dynamics defined for some spin system on a graph of maximum degree data, it will converge in n log n time for all these type of models in the corresponding parameter region. So for example, the easing model, which is one can think of it as sampling from the cuts of the graph, and every cut is weighted by a parameter lambda. And for the easing model, we also get analog n mixing when the parameter is up to the uniqueness threshold. And previously, the ferromagnetic case was known by result of Morcel and Sly, but we managed to show it for both the ferro and the anti-ferro case. And also this generalized to the anti-ferromagnetic two-spin system, which contains both the easing model and the hardcore model. And we show that when your model is up to data you need, well, this is a notion defined by Lilu and Yin. And also for coloring, this is the problem that you are given a graph and you want to generate coloring of the graph uniformly at random. And for the coloring problem, we show that Glauber is n log n when the number of colors is greater than 1.76 times data and the graph is triangle free. So this is the parameter region that matches the previous like methods of the using the decay of correlation or using the zero freeness of the partition function and the polynomial interpolation. So we didn't get like the conjectured threshold, which is q greater than delta plus one, but we match the previous algorithmic results. And finally is the matching, which is the monomer dimers model, where you sample matching, which is with weight given by lambda to the size of the matching. And previously, Jaron Sinclair shows that you always have n-cubic mixing for any graph, means the degree can be unbounded. But for bounded degree, we show n log n with a constant depending on the maximum degree data. And so our results actually, we actually show a very, like the main technical result behind all these theorem is a theorem about that any Gibbs distribution of some spin system satisfy two conditions, then the Glauber dynamics will converge in n log n steps. And so it's a very general result and holds for any pairwise spin systems where the weight of every configuration would describe by some nearest neighbor interactions. And the example would just be the hardcore and all the previous models. So they are all follows in the class of spin systems. And we will assume that it is defined on a sparse graph, a graph of maximum degree data. And we also assume that your distribution is marginally bounded, which means that, and also spectrally independent. So I will define these two notions in more detail very soon. But roughly speaking, the marginal boundedness, just as any marginal probabilities, are bounded away from zero. And the spectral independence is defined by an Aurelio obvious government, which is sort of describing the decay of correlations, but using a spectral way. And also this paper of Aurelio obvious government, so they introduced the notion of spectral independence, and they show n to the eta mixing for the eta spectrally independent distribution. But we managed to improve it for bounded degree graph to the n log n, to the like the asymptotic optimal n log n. And also I want to remark that so usually the marginal boundedness is like a very simple thing to show, and the spectral independence since it has been defined, has been showed for many models, like including the hardcore, the easing, the two spin system, and colorings and matchings. And that's how we basically get the mixing time result for all these models. And so the next two slides, I'll introduce the notion of marginal boundedness and spectral independence. And so I just take like the hardcore model as an example.
Could I interrupt and just ask a question about the results?
Yeah.
Yes.
So for example, in the Ising model, even in the ferromagnetic case, there's a notion of critical slowing down when you get near the critical temperature. And are you claiming that doesn't happen with your model of the Glauber dynamics? So if I take an Ising model and I go to temperature.
Tom, I think they're always safely away from the critical, like
are they
1 minus delta?
Yeah.
So,
but you're near. I mean, beta critical, isn't that the critical temperature?
Yeah. So beta critical is the critical temperature, and we look at when beta.
But you just have to be below that, right?
Yes. Yes. So it's the inverse temperature. So it's
yes, that's fine. I understand. Yeah, you're above the critical temperature. But
yes,
but still, you should still see effects when you get near beta critical.
Yes. So here the n log n should be some constant times n log n, and the constant becomes large when your beta is closer to the threshold. So the constant will.
You're not quantifying that, I guess.
Yes, yes. So in our paper we quantify this, but yeah, so there's some dependency on the constant and all the parameters like the maximum degree and also the distance between the difference of the parameter and the threshold.
Okay, yeah. Okay, well, that's a very nice result. Yeah, thanks.
Yeah, let's move to the definition of marginal boundedness. So this is just a condition that, so basically, I'll take hardcore as example. So it basically says that the probability, you look at the marginal probability of a single vertex, which is the probability it is inside the impedance set or not. And the marginal boundedness just says that every marginal probability would be bounded below by a parameter b. And also this condition will hold under any pinning, where by pinning I just means I will fix a certain vertex to be a certain configuration, like fix a few vertex to be in the independent set and a few vertex to be outside the independent set. And this is just basically considering any conditional distribution, your bound on the marginal holds for under any conditioning as well. And the second notion is the notion of spectral independence. So for this, we will look at, we will define notion of influence from a vertex to another. So basically the influence would just be from U to V would just be you look at the probability if V is in the impedance set or not, given that U is in it, and given that U is not in it, and you look at the difference on the margin of V. So this kind of tells you how much the condition of U would influence your marginal probability at V. And so if you have this influence, you kind of define a matrix per C, and the spectral independence just says that the maximum eigenvalue was bounded from above by a parameter eta, and also the same holds under any pinning. So just means with any conditioning, you have a different influence matrix, and all these influence matrix have bounded maximum eigenvalue. And so our main result would just be that, so for any spin system, including the hardcore or easing or the colorings, so if it's defined on a sparse graph, which is a graph of maximum degree data, and also it is, you have this marginal bound, which is usually very easy to show. And more importantly, this notion of spectral independence, then your Glauber dynamics will converge in n log n steps. And there's a constant C before it, which depends on the maximum degree, the boundedness, and the spectral independence. And so this is like the key result, like, and all the results for like hardcore and easing and coloring will follows from this key result. And so for the rest of talk, I mainly talk about the proof approach and ideas, which uses entropy, tensorization, and factorization. And also we use like viewing the Glauber dynamics in the framework of simplicial complex, and some local to global argument for entropy contraction. So is there any questions so far about the results, and before I go into the proof techniques? Yeah, so maybe I go on. So I try to just give a very rough idea, like how we establish our result. And so basically we will try to establish the decay of relative entropy, and establish the modified locus overlap constant. And so just to give you some, so I just first like define this notion of relative entropy, which is a standard thing in the analysis of Markov chains. So for any function f, I'll use the expectation of f to represent when you generate a sample, and the expected value of the function f, and the entropy of f would just be the expectation of f log f over expectation of f. And so this entropy, so if you are not familiar with it, it's kind of describing the fluctuation of the function f with respect to the distribution mu. So in particular, if your entropy is 0, and then your function f will just be a constant function. And also, if your function f is the relative density of two meshes, then this entropy will just be the KL divergence between the two distributions. And also, I will try to look at a notion of local entropy. So this is entropy, the notion of entropy defined with respect to a single vertex. And so I take a vertex V, and I take opinion of all the other vertex, and this defines a certain marginal distribution at V. And so if I'm given the function f, then I can define the entropy of f with respect to this conditional measure. And this will define a notion of entropy locally at this vertex V. But this also depends on the pinning, the boundary conditions on all the other vertices. And so what I do is I take expectation over it. So you basically take a random boundary condition and look at the entropy locally at this vertex V. And this in some sense describes the average local fluctuation of the function f locally at V. And so the reason of defining these two notions is that there's also this property that's being studied, which is called the tensorization of entropy. And more specifically, I will study the approximate tensorization, which basically says the entropy of f would be upper bounded by the sum of local entropy at individual vertices given by parameter C1. And so this approximate tensorization was known like to hold for the product measure with an optimal constant C1 equals 1. And so this is a very well-known fact, which says that any product measure will satisfy tensorization property for entropy and for variance as well. And what's important for us is that this notion of approximate tensorization, if you know it with some constant C1, then it immediately implies n-log-n mixing for the Glauber dynamics. And also, it actually implies the modified log Sobolev constant for the Glauber dynamics. So I won't define it in detail, but it's also some standard functional analysis inequality to analyze Markov chains. And so this gives the notion of the approximate tensorization for the entropy, which describes the property of the measure. And also I want to study another notion, which is the factorization with respect to all subsets of fixed size L. And this is like motivated by another like heat bus type block dynamics, which unlike the Glauber dynamics, so for Glauber dynamics, in every step you pick a vertex and update it. But in the block, like the L uniform block dynamics, what we will do is that you pick L vertices uniformly at random, you update the state of all of them together, conditioned on everything else. So for the hardcore model, it will just be you pick L vertex and you decide them together, which of them are included in the impen set and which of them are not included. And this is the block dynamics. And also you would have this notion of a block factorization of entropy, which basically says that the entropy will factorize into the local entropy at every subset of size L. And if you look at the notion, And you will see that if L equals 1, then this is basically the same as the tensorization. But what we will mainly consider is the linear size L. So basically, we will update a linear subset of vertices. And this is inspired by the notion of general block factorization by the recent work of Caputo Parisi, and also the views of simplicial complexes by the work of Anari Liu-Vias-Garin. And in particular, this one basically for simplicial complex, as they basically consider configurations on a subset of vertices, which is would exactly be this notion of L uniform block factorization. And also you have this property that this factorization holds with optimal constancy equals 1 for product measure. And so what we will show is that if you have the uniform block factorization.
Can
Yes.
you go back to the previous slide?
Yes.
So you said that your global dynamics will use this L block transition where you update a linear number at every step, right?
Yes.
Yes, but this should be computationally hard to do unless the set of vertices you picked at random is mostly independent. Only then can you put the marginal, right? Otherwise,
Yes.
maybe computationally hard to even assign to pick the new state.
Yes, that's right. So, but so we only consider this chain for the purpose of analysis, but we are not actually running this chain.
Okay.
And so actually we only what's important for us is basically this notion of factorization of entropy, and we are not directly looking at this block dynamics, and just for the purpose of analysis. And the reason is that we will show that this block factorization would implies the constant, the approximate tensorization. So this, in some sense, provide a comparison between this Glauber dynamics and the block dynamics, but we are not directly analyzing this block dynamics. We just use this as an intuition for comparing these two notions of factorization for the entropy. And also this comparison will hold for variance as well, which would corresponding to comparing the spectral gap of these two chains. And does not compare the modified log-Sobolev constant, but is good enough for the applications. And so just some high-level approach of proving it. Basically, just the proof is actually not hard. And the idea would just be you pick a sparse linear size subset, then reshatter with high probability. That just means you will have like many connected components, and each of them is constant size in expectation. Then the tensorization on this sample, the entropy at this subset will tensorize to every component, and every component is like constant size. So that's how you show from a small linear size blocks to tensorization for every vertices. And also, so basically that's where we use the maximum degree condition, the sparseness of your graph. And so from the sparseness, we can show block factorization to the approximate tensorization. And also the rest of the talk, like the rest of the proof, will be using the simplicial complex and the high dimensional expanders, and using the spectral independence to establish this block factorization of the entropy. And so let me just, don't think I have too much time, but I'll go very, that I just give some basic ideas for the simplicial complex and how to use that for the Glauber dynamics. And so the things here are mainly following the results of Anari Liu-Vias-Garin. And what they do is they look at the Glauber dynamics as a certain dynamics from the subset or from the set of all full configurations to the set of all partial configuration on one less vertex one less vertices. And so you start with a full configuration, like every vertex assigned a value, and you go down to a partial configuration, pick uniformly at random, and then you try to go back to another full configuration, but this time you update with the correct conditional marginal probability. And so this kind of, you view the Glauber dynamics as some random walk from the subset, from the family of full configuration to family of n-1 subset configurations. And also you can do more. So you can look at like the subset, the collection of all configuration, partial configuration on two vertices, and all partial configuration on single vertex. And you can define a dynamics from these from partial configuration of size 2 to partial configuration of size 1. And the dynamics is similar. So every time you first drop a vertex, which you pick uniformly at random, and then you go back. But when you go back now, this time you need to first pick a vertex, like decide which vertex to add it, and then decide the spin or the value of this vertex, and you pick it with the correct marginal probability. And you can define also, there's the chain from level 1 to level 0. So level 0 basically have nothing, so the chain becomes just a travel chain. But so this notion, so this type of view actually become lies in a special class, becomes a special class of the so-called the simplicial complex. So I define so this is certain, a special case of abstract simplicial complex, which is a pure n-dimensional weighted simplicial complex. So basically, it well contains, so n is the dimension, and it well contains xn, which is the collection of a few size n subsets of a ground state U, and pi n will be a distribution. And for every k smaller than n, we will have xk, which will be the collection of all size k subsets of the sets in the top level, and the pi k will just be the distribution when you draw a subset from the top level and take a random subset. And so if you want an example, you can just think of it as the matrix, where xn will just be the n will be the rank of the matrix, and xn will just be the subset of all the bases, the set of all the bases, and xk would just be the set of all the independent set of size k. And so this will just give like a full picture for the simplicial complex, for the Glauber dynamics or spin systems in the view of simplicial complex. And so for the simplicial complex, we study this notion of the entropy contraction, which for every function f defined on the top level, we can define a projection of fk, which is the projection of the top level function to a lower level. And we study how much does the entropy contracts. And this has been studied for matrix. And what we show, or an amazing fact, is that for spin system and the simplicial complex corresponding to the spin system, like the hardcore model, this notion of uniform block factorization of entropy would just corresponds to how much your entropy contracts when you project from the top level to a lower level. And so if we have that, so what we do next, we use some this standard.
Wait. So don't rush. Can you go back to the entropy contraction?
Yes.
Right. So this is a projection from the top level to some intermediate level k.
Yes,
Yes.
yes.
And what's the relation between k and n? It's a constant
Uh,
fraction. K is a
oh,
constant
so
fraction.
so you mean this kappa, right?
No, the
So the
k.
kappa will be
The
the rate
k.
of
What is k? K is a constant fraction of n. What should we think of it?
so so the k would just be like the level you are interested in, and so n is the top dimension, like n will just be the top level,
Yeah,
and the k is the one you are interested in,
yeah.
and so for our case, like what we will study like k is basically linear in n, and we want to study how the entropy contracts when you move from level n to level linear in n for some constant c, so level cn.
And what
And
is the kappa then? How is kappa related to k?
how kappa relate to k? So so yeah. So what we will do next will just be like to establish the relation of kappa to the k, and it will depends on this. So it will first depends on this local entropy contraction, which is the entropy contraction in the simplicial subcomplex, which further reduced to the spectral independence. So this kappa would be a function of all the spectral independence constant. And if you look at a general simplicial complex, it would be a quite complicated formula actually. But for spin systems, you can simplify the calculations, and the so it would just basically be like I think it'd be something like this, but that's for like in our notion, something like this I think. So that but this kappa would be this will be a kappa for the for spin system with a spectral independence property. But for an abstract simplicial complex, the formula is a little bit complicated in general.
Okay.
Yeah. So the reason is that we will look at, so we use this local to global argument, and for every local entropy contraction, we have it corresponds to this local spectral expansion. So this contraction ratio will be a function of all the local spectral expansion ratio, like. And also, so basically the previous work of Anari-Liouville and which uses the simplicial complex results of Aleph law, they did it for variance, and they go directly from the spectral independence to the tensorization. And so this is basically the AL20 and AL020 did. And they did like into the order eta, which is a large polynomial, but if we use this also connecting to the block factorization of entropy and tensorization, we can improve it to the n log n. And yeah, that's like the idea of the proof. And just to conclude, we show the Glauber is n log n for many spin systems, and open problem would be a better dependency of the constant on the parameters like the maximum degree and the marginal boundedness and the spectral independence. And in particular for hardcore, our bound is exponential in data. And also for coloring, can we do like the big conjecture is like q greater than delta plus one, and can we do the sampling? And that will be all for my talk. Thank you very much.
Thank you very much. Okay, questions to Zongchen?
Yes, Zongchen. Thank you for a terrific talk. That's great stuff. Can you post the best reference for your stuff? I found a paper online that starts with optimal mixing and another one that starts with rapid mixing. What's the best place to read what you told us about?
Yeah. So for this result, for if you do spectral independence from spectral independence to the mixing time bound, it will be our paper, like the paper of me, Hui Liu, and Eric Vigoda, in the name of like optimal mixing of Glauber dynamics, the paper of the same name of my talk. So that paper, we establish the from spectral independence to the mixing time bound. And there's also, let's see, oh, I think, yeah, sorry, I have a glitch of the computer. Yeah, there's also a few papers which do establishing the spectral independence. So there's paper like, yeah, let's see if I can.
But Peter, you were asking about this result, right? You were asking about the best place to read about this result, Peter.
Yes.
Yeah, so this result, he told you, this joint work that, yeah, optimal mixing.
Yeah. So it's the paper would just be the name of the title of the talk.
So this is in, I found this in Archive 2020, but you said something about 2021. Has it appeared somewhere?
Yeah, it will appear in the stock. So I write 21.
It's the same paper.
Okay.
Yeah, the conference next year, this year actually. Yeah, but it was on Archive last November.
Okay.
Can I ask a question?
Well, Jin Yang wanted to ask a question.
Oh yeah, so is it right that the hard part is to show the spectral independence, and then so does that mean once we show the spectral independence for some other models, the models other than what's mentioned in your talk, then that means we can show the bound in your paper also work for those other models?
Yes, that's right. So what we show is that if you have spectral independence, then you have analog mixing. So yeah, if you can show spectral independence for other model, then you can apply like our result. And but there's also other thing like improvement from our result. That will be to get better dependency on the parameters for the constant. So especially for the dense graph, like the maximum degree is unbounded, then like our results, like our dependency on maximum degree is exponential in some cases. So you might still need some improvement, but that's like for dense graph.
Okay, thank you.
More questions?
Hey, can I ask a question?
Yeah, well, nice to see you.
So I'm trying to compare your like general result about spin systems to what you get from the Bruchian condition. And if I understand correctly, like there are two main differences. One is the usual results regarding the Bruchian condition. You add this influence matrix that you consider. So usually you have to look at like the operator norm, not of the matrix itself, but of the matrix where you take like the absolute value of the entries. And if I understand correctly, you don't need to take absolute value, which is kind of like much stronger when you have negative interactions. The operator norm can be much smaller. And I guess that's like crucial for you.
Absolute value. No, Zongchen, you have absolute value in the spectral matrix or not?
So the influence matrix itself, every entry does not have absolute value, so it can be positive or negative.
And I think
And
that's like crucial, right, to get tight results for sampling independent sets, or or it doesn't matter so much?
So currently, like our proof for the spectral independence, we actually still use some of absolute influence. So currently, it doesn't really matter if there's
Okay.
or not.
So
But,
okay, so in that case, why can't you just use, if you just use, you know, off-the-shelf Dobrushin condition results, do you just get a worse constant for the, like, the threshold for which you have fast mixing, or?
Yeah, so if you use the Dobrushin uniqueness, you don't, like, for hardcore, you don't get like up to the uniqueness threshold. You get like up to the Dobrushin
Like,
which
is like, and the difference between them is just like a multiplicative constant, like 2 or something, right?
Yes, yes.
I see. Okay. So if I want to only get to like half the, like twice the critical temperature, then okay, then like all those off-the-shelf results. But still, if I compare to the Dobrushin condition, it's like you don't need those absolute values, and it, like, okay, you don't really use this, but your general theorem doesn't need this. But what you do need is, like, for any pinning of like the coordinates. So I guess those are the, okay. And I have one more, like, I'm not sure what the question is exactly, but it's kind of strange that, like, the theorem you get. So, okay, if I look at your analysis, it seems like the size of the current size of the independent set along the random walk plays like a very important role, because I guess you have, you know, all those restrictions to these like sections of the cube, and you just go one level up and down, and the analysis really relies on the relations between those sizes of sets. But in the end, like, the theorem you get doesn't have anything to do with those sizes. I mean, in a sense, I guess, okay, Glauber dynamics only changes the size by 1. So my question maybe doesn't make so much sense, but it seems to me like the framework you get doesn't have to really concern. So, like, the 1-1-1 direction doesn't have to play a special role in those theorems. Do you see what I mean? Or maybe I'm...
Yeah. I think I kind of, I think you say, like, the analysis consider like k vertices or large blocks, but I mean, eventually you only study like single site Glauber dynamics. And yeah, I think a partial reason was that, like, we kind of combines like 2 types of the proofs. Like, for one side, the simplicial complexing, which works but doesn't gives you n log n. It gives you a large polynomial. And meanwhile, the reason of that is that the analysis is kind of not tight when you are close. That means when you are up, like, single site, you update single vertices, this notion of spectral independence and like the local spectral expansion in the simplicial complex framework is not tight. And I think the reason is that you consider the worst pinning, like you want this maximum eigenvalue bound for holds for any pinning, but it might be like you shouldn't do any pinning, but in some expected version. And meanwhile, there's also this notion of tensorization and entropy factorization, which kind of solve this problem when you are close to the like when you are update less vertices. So I don't know if this answers your question, but
yeah, I didn't completely follow, but I'll just have to look closer, I guess.
I don't know if you saw other analysis. Maybe Cynthia can answer this better. But if you've seen previous analysis of Markov MCMCs or global dynamics using eigenvalues as opposed to divergence, you also have seen that this is only in the analysis that you look at the the restricted walks in the queue between levels k and k plus 1, but you use this or you build inductively as a good spectral gap for the one you are interested in. It's not happening in the Markov chain itself. It's just a way to analyze the convergence of the spectral gap of the Markov chain. It's not actually happening in the
sure,
algorithm.
fair enough.
So what is being, I mean, I don't know, I see it first here, or maybe it was done before, but that the same, or the idea of local to global analysis happens instead for spectral gap, it happens here for divergence, and this allows you to get a log Sobolev constant, which can be better for convergent proofs than spectral gaps. And I guess you should correct me, Zongchen. I think because you get a log Sobolev constant, you get a better bound on the mixing time.
yeah, so we get it for entropy, and which actually corresponds to the modified log Sobolev constant. I mean, which also after like a constant factor, you get the log Sobolev or log Sobolev constant. Yeah, so
I guess if it was just spectral gap instead of n log n, it would be n squared, right? It still would improve on
some polynomial, yeah. But this was known. This was known in the previous work of Anari and of Esgaran and Quick-Liu.
I thought it was like n to the 1 over delta or something. Okay, I don't know so much.
So the Anari the Anari Liu Esgaran, they did it for the variance, and they didn't do the like the tensorization of entropy and the factorization of entropy, these type of things. They just took the simplicial complex point of view and use this like recursive or inductive way to bound the gap of the chain. And if you do that, you get n to the eta for this eta here. So it won't give you the n log n. And I think the reason is that this eta is not tight when you have many pinions. And I mean that at least that's how I think about it. Yeah, and they did it for gap, but so we did it for entropy. So there will be some technical issue to deal with, but the high level ideas is similar.
Okay, more questions?
Yeah, I just have a question about whether you have, this technique seems to work for ferromagnetic, anti-ferromagnetic, right? So you're quite robust, but the ferromagnetic cases should be somewhat simpler. Do you see that in your work or not?
Yeah, so yeah, like for the ferro case, there are some like for ferro using there's previous result or ratio n log n. So our result does not uses the ferromagnetic and does not use any property of that, like the monotonicity of the system.
Yeah.
And we kind of for all, like doesn't matter if it's a ferro or anti-ferro. And we
so what about something like an XY model? I don't know whether you're familiar with those. An XY model where the spins take values in a circle or something like that.
Oh, yeah, we haven't look at those. Yeah,
because
yeah,
those are, I think they're, even in the ferromagnetic case, they're not, you know, you get up to the de Bruijn threshold, but I don't think people have any work that goes beyond that. That's my impression.
I see, but I think the difficulty of, I think now given our work, the difficulty would be like establishing the spectral independence for these type of model.
Yeah.
12:36.
I'll be right behind. Okay, thank you very much.
Sorry,
I have to go. Thanks a
Can I
lot.
just
Very
one
nice.
last quick question? Sorry.
Yeah, go ahead.
It's so the fact you're not using the fact that the like influences can be negative, but it seems that this might also be useful for spin glasses if like your condition kind of knows how to take into account the sign as well. Do you know if there is any application to like non-trivial application to spin glasses?
So yeah, so establishing spectral independence. So I think currently all the examples of all these type of example, we basically consider the row sum of this matrix, which corresponds to the sum of influence in absolute value from a vertex V to all the other vertices. And yeah, so basically that's what we consider like in all these previous works. But I don't think, personally, I don't think that's the best thing, because I think eigenvalue would be the better, like the maximum eigenvalue itself would be the better things to analyze. But I don't know if, yeah, I don't see any example yet, like analyzing directly the eigenvalue of this matrix.
Like if I just try to use it for the SK model, where, you know, the entries are, you know, just Gaussians over root n, then, you know, there is a big difference between taking the spectral norm and taking the spectral norm with absolute values, or just the sum of absolute values over the rows. So it seems that like already this is what I'm trying to understand. For the SK model, does it give some non-trivial mixing time? For what temperatures would it work?
Yeah, so I think currently our results, like our framework does not work for SK. And there are multiple reasons. And first thing is that like we need this to hold under any pinning. And I think so given an instance of the SK model, like you can make funny pinning to increase the sum of weight neighboring like edge weights. And that might ruin the notion of spectral independence. And also there's the reason that the unbounded degree, which we cannot deal with. Like we cannot even deal with the mean field, like the complete graph. So yeah, I think that's the hard question, like for our framework or proof approach.
Cool, thanks.
Avi, you're muted.
Thanks. I was muted. Okay. Thanks, Zongchen. So it seems like, yeah, everybody who wanted to ask a question asked. Great. Thanks a lot.